You see, this course is advanced and something. Now I think that I will show you these advanced things, because most of the presentations that I showed you is more or less standard alpha or gamma spectrometry related things, but these are that I present you, these are quite new things. And I only talk about recent development in my institute. And this is important. Sorry. Do you know what's this event mode or list mode data acquisition? Have you heard this concept before? All right. Sorry. I will explain you soon. So we have several quite modern equipment in stock. We have alpha gamma coincidence systems, Compton suppression system, and a cosmic ray background reducing system. Let's look at the basis of the event or list mode data acquisition. What does it mean? All right, the point is here. So, single measurements, by using gamma ray spectrometry, for example, it does not necessarily give all the information needed for complete characterization of a sample. Like those nuclear bomb particles that there is another possibility. I mean, the possibility is this one. Now I assume that I am a multi-channel analyzer, and I am not now looking about the data that is coming from the measurement system. Okay, channel number 1 may contain 0 counts. Channel number 1 may contain 2 counts. Channel number 2 may contain 7 counts. Number 3, 0 counts, etc. Up to 16,000 counts, if I was correct, it was in this system, or 32,000 counts, channels. I don't remember now the exact number. Was it 32 or 16? How? 16, I guess so, yeah. All right. Now, same thing holds also for alpha spectrometers, but I think that the number of counts was here different than the 16. I don't remember, was it 1,000 or something like that? But anyway, if the number of channels are equal or not, it doesn't have an influence here. But the point is, if I put for these counts, these 2 photons that are, for example, this channel, if I put time signal, each of them, for example, this case, there is some time signal T1 and another photon signal T2 in terms of microseconds, of course, because the pulses are and clocks are very accurate. All right? Why to put time signal there? Because if you register only a spectrum, amount of data is not very big, in fact. It's, in your case here, it's 30 kilobytes around, or 100 kilobytes. But if you put signal to each photon, you make it out you can apply so-called software coincidences. You can later combine these two methods. So it's post-processing the data instead of tedious hardware coincidences. I will explain this more. So, coincident spectra can be generated from the time-stamped data online or in post-production. So, you can see here, this is the sample. This can be gamma ray spectrometer and this can be alpha spectrometer. It emits data to both of these systems. So, access to time-dependent behavior of the measurement system that would have been invisible under normal histogram recording. This spectrum that you see on the screen or on the paper. So, the point is that the detectors are running with a synchronized clock. This is important, so that coincident or anti-coincident events can be selected from the data using post-processing. So, signal in both detectors within a short time window, they both come from the same event. It's possible to select between events that are anti-coincident or coincident, or fall within a specific energy window in another detector. Let's see some examples here. This is, again, animal name. You remember this ASI software, donkey, and bull, car. Now this is panda, developed in our institute. So this is seems to be a very complicated system, but basically there is a gamma spectrometer here and a alpha spectrometer in this vacuum chamber. All other things are not very relevant from this point of course. So, particle comes, panda name comes for the words particles and non-destructive analysis. So, you know that if you are using alpha method, then you have to destroy your sample by radiochemical means usually. But we don't want to do that. We don't want to destroy samples. So, this equipment uses position-sensitive alpha-gamma coincidence techniques for measuring environmental samples. So, there is one so-called vacuum chamber for loading the samples. It is in fact shown here. You cannot see the sample, but it goes this way into this vacuum chamber. And there is another vacuum chamber for the measurement, this one. In this case, there is no lead shielding. Why? All right, you will see it. Which is in fact not a very good thing in practice. You will see that. There is no nitrogen cooling, it's electrically cooled system, this one. This is a gamma spectrometer. Let's look at this in a realistic way. So, The measurement setup consists of one high-purity germanium detector for gamma rays and so-called double-sided silicon strip detector for alpha particles. And pixel size for that detector is 3 times 3 square millimeters. So it can locate where is, for example, a hot particle in the sample. This spectrometer strip can record an alpha spectrum. The sample, for example, a nuclear bomb particle, it's shown in the next slide. It is located between the detectors. Let's forget this because this seems to be quite complicated. I will show you the principle, which is more important here. So let's begin here. Picture A. So it's a measurement setup here. So this is gamma detector here, and this is the alpha detector. And the sample is located between these two detectors. So in our example, it is a nuclear bomb particle from Thule. Do you know this Thule accident? This place is in Greenland, at very north. And I think it was 1970s or 60s when a big nuclear B-52 airplane crashed to the ice of Greenland. Fortunately, that plane was carrying nuclear bombs. Fortunately, these bombs were not exploded like nuclear explosion. Of course, they broke down, and the material went to on the ice. And when the ice melted, it was sea ice. Then the material came to the bottom of the sea, not very deep. Some Danish colleagues gave us these samples, and we analyzed them some years ago. So this is one nuclear bomb particle. This one, it's non-detonated particle, so there is no nuclear explosion. It's like raw material. You can see this is the alpha detector. You can see the strips here or this way. So each strip can detect an alpha spectrum. And you can see here number of counts for the strip 6. The horizontal strip, this one here. And this is the vertical strip here. So we can see the location of the particle. So remember that this is 3 millimeter size of each strip. Now, figure D is this one, yeah. I have to read it. It's a singless spectrum, means raw alpha spectrum. And the red, or this one, it is 59 kilo-electron volt americium peak gated alpha spectrum. So we selected a narrow gate in the gamma spectrum, for example, from 55 to 65. This narrow area, and generated alpha spectrum from the data shown here. So these are this coincidence spectrum. So it can show, you can see here some counts, not very many in this case. Counting time was so small. But these are only americium, nothing else. In normal alpha spectrometry, you see this kind of spectrum. And you have to do spectrum analysis to calculate, for example, how many alphas, how many alphas come from americium, for example. But now we can see it clearly that these are only from americium. In this case, picture E, it's a singless. Singless means it's a raw spectrum. It's a singless alpha spectra. It is this black one here. And I guess that the background, it's this gray one. Sorry, there are no colors in this picture. This is a singles normal gamma spectrum here. This spectrum here. What you can see here is only very, very small peak for americium. When we gate this spectrum by using alpha, we get out this kind of spectrum. See the count rate level. There are almost 100,000 counts per channel here. But there is no background at all, basically. So we can very easily detect what are these peaks, which cannot be identified, not at all here, in the raw spectrum, so-called single spectrum, normal gamma spectrum. From the same spectrum, we look through area from 180 to 190. So we try to look around, are there any uranium-235 signal present? In this case, in the normal spectrum, we cannot see nothing. However, now we can see that there is definitely uranium present in that nuclear bomb particle. Not only plutonium-239. You know that in nuclear bombs there are two main isotopes in fission bombs. Plutonium-239 or maybe 235 uranium. And it's because of the post-processing and putting the time signal to each event. Then, because this PANDA system was very complicated, because it is able to locate radioactive particles in the sample, so I suggested my colleagues that could we do it much more simpler way, and we can do it. Let's look at mini PANDA in this case. So mini PANDA system is basically, it's very easy. So you can see the gamma detector here. It's electrically cooled here. This is lead shield. Now in this case there's lead shield and there's an alpha detector here on which we can put the sample. Thin sample, of course. Because if we are using thick samples for alpha detection, it's not a good idea. So we can use this system for air filter measurements. In this case, there is no position sensitivity. And it operates at ambient air pressure. So these are like normal alpha or gamma spectrometers, but now we put them together and used this list mode technique. Let's look at the detailed picture. So this is lead shield, this one, gray one. This is electrically cooled gamma detector. This is alpha detector, and we substitute the sample between these two. This alpha detector is so-called CAMBIPS, which can be used in normal air pressure. So what happened here? I didn't do this, but my colleagues did. So a sample was prepared by depositing a droplet of solution containing radium-226 and cesium-134 onto a glass fiber filter. And then a Muller foil, very thin one, was placed above the sample to prevent contamination, especially for the alpha detector. And this is the spectrum recorded by the alpha detector. So you can, when we put radium-226, it was liquid, of course, but it generates, as you know, by decay process, radon, polonium nuclides. All of them are visible there. This is the same spectrum. I will show it once more. So this is linear axis here. Now let's look at the logarithmic axis. So, as you know, alpha particles ionize strongly, so it is possible to detect them efficiently, but they are easily absorbed by intervening material. In this case, we have a controlled sample geometry. And alpha spectrometry is, in fact, in many cases, in some of the nuclides, much more sensitive than gamma spectrometry. So this is the same spectrum. I analyzed this spectrum by one of our software analysis softwares. Now you can see the different nuclides present there. So we can analyze also these kind of spectra. Let's see what happens when we are doing coincidences. Again, list mode coincidences. Time signal is collected from both detectors and attached to each quanta. So this is a raw, so-called raw gamma spectrum, normal gamma spectrum. This is gamma spectrum that is gated using alphas. So here we record gammas only when they came same time to the detector, when alphas go to the alpha detector. Again, no background, practically no background. So we can easily see low energy peak. So the method efficiently filters away the gamma background. So, sorry about the noise. Why
the lower side is a little bit, peaks are not well resolved?
Yeah, you mean this area? Yeah. I think that I don't remember exactly, because personally I didn't do this measurement, but I guess that you might know that that because there is radium and cesium emits betas. and also low energy gammas, or practically X-rays. So alpha detector can detect also those. And I think this is the reason why there is larger amount of counts. In this case, this is the same spectrum as shown here. This one. So without doing any spectrum analysis like here, this is analyzed spectrum, but if we don't have a good analysis program, so what can be done? We can select from the gamma spectrum this peak, radium peak. You have to note that the peak radium intensity is normally it's very low. It emits only intensity is 3.5%. However, we can in this case detect those alphas when these gammas are detected at the same time and register, in this case, alphas only. So these are definitely radium 226 alphas. Nothing else. So it's this area here, red one. No background here. Okay, now this is quite difficult picture. This is the same sample again. You can see the nuclides and peaks present in this sample, and we identified what kind of peaks are in this spectrum. But now you can see here, this is gamma energy here, and this is alpha energy in the vertical axis. Now these are not spectra, but we put color signal. How many alphas or gammas we detect? For example, as you know, let's look at this example. This is energy, gamma energy is 200 up, 100 up to 900. So as you know, lead 214 emits these gammas. You analyze these gammas in the lab. So here you can see that you can see the peaks here, 3 peaks, but they are not located here at the energy of 4 or 5 MeV. This, for example, this case shows that there is radon peaks also. So this is very complex way to analyze the spectra. But we will have a lot of information that we cannot obtain from by using only gamma spectrometry or only alpha spectrometry. We can combine these two methods. So another example from miniband measurement from an individual particle containing americium and plutonium. This is in the low energy part of the spectrum. This is the raw spectrum, blue one. And now this spectrum here is alpha coincident gamma spectrum. We clearly, for example, these very small peaks here, or this one, which cannot be identified from the raw or normal gamma spectrum. And these are the minimum detectable activities for gamma, singless or normal spectrum, and alpha coincident measurements as a function of time. So, sorry. This is time here, and this is minimum detectable activities in terms of becquerels. So in the beginning of the measurement, this coincidence techniques has no big relevance because there are practically no counts in the raw spectrum and also in the coincidence spectrum. But when the time goes on, then there is a difference. What about this Compton suppression device? You know Compton interaction already. So we have one system in our institute. So Compton suppression techniques allows to reduce background from the sample itself. Typically energy is higher than 200 kilo electron volts. So about the name of this Kossu, I have to say you that this is not an animal. This is a name of an alcohol drink. I don't explain this more, but it has some specific details. All right. The idea is this. So we have a germanium detector here, standard detector, surrounded by sodium iodine detectors. And outside there is a lead shield. It's a normal lead shield, nothing else. So why to do this? Sample is located here. Let's see. So normal detector surrounded by sodium iodine. All right, I explained this already. Let's go to the next slide. I already explained this to you, so perhaps we can neglect this one. So you know germanium is a semiconductor, electrons, holes, we can detect the signal. However, in case of scintillators, the light is changed to electrons which are multiplied, and then we get signal out from these sodium iodine detectors. So, quantum continuum. So, it's this area of the spectrum. So, I repeat this because there might be some questions in the examination, I don't know. Let's see. It's an inelastic scattering of gamma photon. As you know, gamma can be scattered and electron moves like this. So only part of the original energy of the incident gamma is transferred to the medium. But this is the relevant thing. Part of the original gamma photon energy is lost. if the scattered photon escapes the detector. So, and these Compton scattered events cause a continuous spectrum at energies less than the main photon peak. This is the full energy peak. This. The point here is that when there is Compton phenomenon, it can overwhelm weaker real gamma peaks, which might be present here, but we cannot identify small peaks. So, about this Compton suppression system. So, sensitivity can be improved by selecting only good events. In Compton suppression, the signal of the germanium detector is rejected. If there is a signal in these sodium iodine detectors, this is lead sealed here. So we reject signal in germanium when we detect signal here. And many of these events are Compton scattered gammas escaping from the germanium detector. And this is, if we filter out the coincident events, the Compton continuum can be reduced by enabling better identification of real peaks. Of course, some nuclides have coincident production of gammas or X-rays, which can cause reaction if they hit the scintillator. But let's see the effect. The effect is this one. So the green one is normal or standard gamma spectrum. And if we react those events, if there is a signal in scintillation detectors, then the background is lower. And perhaps we can see signals, weak signals, much more easier. This is the idea for Compton suppression. Not very difficult. So, one more system. We can reduce the cosmic ray background by using this system. So, as you know, cosmic rays are coming to the ground level, and we can detect these signals in gamma ray spectrometry. But in this case, scintillation detectors are outside germanium. And we react the gamma signal if we have signal in one of these scintillation detectors. So this system is also operating in list mode. So this setup is already completed. It's not yet fully tested, so I will not show any pictures on that. So, as I told you before, this was advanced lecture on alpha and gamma spectrometry, and these are advanced things. Sorry, I had to present these, but now I hope that you get or will get some new ideas how to improve your systems. You have already done that. It's great, but let's see what happens in your laboratory. So thank you very, very much listening my presentations. I hope that you understood something. Even though my intonation is totally, English intonation, English speaking is totally different to you. You are speaking so fastly, which means that I have sometimes difficult to understand you, but I'm learning. So Thank you very much.